Long ago, in a time forgotten, human beings immersed themselves in the world of knowledge through the simple yet profound acts of reading, listening, and engaging in meaningful conversation. They gathered together, sharing stories and wisdom, their imaginations fueled by the written word rather than glowing screens. Libraries were sanctuaries of thought. Yet, amidst the digital din, a treasure trove of footage has been unearthed, revealing glimpses of this lost era, a time when curiosity was sparked by human connection, and the pursuit of understanding flourished in the quiet spaces of life. Or perhaps this is simply a myth. Perhaps none of this is real. Perhaps this is a simulation. Perhaps you are a cog in a chaotic system.
Fits. 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 Welcome in, everyone. Find your seats. That's right. I'll be with you all in a moment. Just go ahead and settle down. Find your seats. There will be plenty of time for existential dread here in a moment. All right. Welcome back, everyone. Nice to see. I see some familiar faces here. Some of you had my intro level classes, but now this is a whole new ball game. Welcome to Advanced Physics. I'm Professor Acoustic, and today we're going to be jumping right into things. So, hope you're ready to take some notes. I'll have some assignments for you at the end of class today, and I understand if a good 20% of you decide to drop this at the end of that drop. Why don't we get into the roll? Atoms. Here. Allard. Belt. Here. Bell. Chase. Dandelion. It's a rather interesting last name. Fitz. Fleck. Gander. Glenn. Hansen. There you go. Jankowski. Kowalski. Landry. Mendelssohn. Nancy. Yeah. That's a drop. Got that email earlier. Pendleton. Caressa. Endelman, Ruddles, Sanderson, Sands, that's another drop, Towson, Vardas, Vargas, Yancey. That's all. All right, most of us here present and accounted for. All right, if I could, I'd have you take out your textbooks and go to page 15, please. Page 15, section on Understanding Poetry by J. Evans Pritchard. No, I'm just kidding. This is not the Dead Poets Society. This is advanced physics. So we're going to be talking a little bit about chaos theory today. Has anybody here heard of chaos theory? If you have, please raise your hand. A couple of you. All right, hand up. Tell me what chaos theory is. All right, sort of. And I would say you're not completely off the track there. Anyone else? Okay, so chaos theory is a branch of mathematics and physics that focuses on the behavior of dynamic systems that are highly sensitive to initial conditions. This is commonly referred to as the butterfly effect. Has anyone seen that film, mid-2000s, Butterfly Effect? No, of course not. I'm kind of dating myself here. But chaos theory demonstrates that within the apparent randomness of chaotic, complex systems, there are underlying patterns, okay? Feedback loops, self-organization, things of that nature. The theory has applications across multiple fields, including weather forecasting, physics, engineering, economics, biology, and even philosophy. So I think the best illustration of this, before we get into some of the more heady definitions, has anybody here been to the ocean before? Raise your hand. Has anybody seen an ocean wave? Right, naturally, yeah. Has anybody seen the same ocean wave twice? No, I mean, if you were to have the break of an ocean wave modeled by a series of numbers, maybe it's just in binary, or maybe it's a series of calculations that represents how each part of the wave breaks, we would be able to quite confidently say that no wave has ever broken exactly the same way twice, but we all know what an ocean wave looks like, and we've all seen it. We know exactly what an ocean wave is, despite the fact that you've never seen two of the same thing before. It's a perfect expression of a chaotic system. Now, the term chaos can be misleading, and I think that's what throws people off. It suggests pure disorder. In reality, that's not what it is at all. Chaos theory deals with a type of order that appears random but follows deterministic laws. So it is a seemingly random or chaotic part of an ordered system. This means that chaotic systems are predictable in the short term, but impossible to predict over extended periods due to the cumulative effect of small and sometimes minute changes. In other words, chaotic systems are deterministic, but not predictable in the classic sense. So let's go back to the ocean wave. Chaotic systems are deterministic. We know that the ocean wave is going to break. We know generally what it's going to look like, but not predictable in the classic sense. We are not going to be able to tell you exactly how it's going to break, where it's going to run, how long it's going to run, exactly how large it's going to be every single time to the most minute of details. We can't do it. All right, so write that down. Chaotic systems are deterministic, but not predictable in the classical sense. Now, let's get into the historical background of chaos theory. I know, everyone's favorite. Now, the development of chaos theory began in the early 20th century, but it wasn't until the work of mathematicians and scientists like Lorenz and Feigenbaum that the field came into its own. Okay. It was Henri Poincaré that noticed the sensitive dependence on initial conditions in this study of celestial mechanics, a precursor to more formalized chaos theory, right? So, and again, It's really important to talk about initial conditions when we are referring to chaos theory, right? It's very, very important. The field began to gain some momentum in the 1960s when Edward Lorenz, a meteorologist, developed his own system called the Lorenz system. Something you might want to write down now, the Lorenz system. That's Lorenz, Lorenz system, while studying weather prediction models. Now he discovered that even a minute difference in the initial conditions of a weather model will drastically impact results over time. So that led him to realize a few things. Long-term weather forecasting can never be entirely accurate. So forecasting, the longer you go, the more inaccurate it is. I'm sure you've noticed that in your own lives. However, short-term forecasting, much more accurate. Why do you think that is? The initial conditions, right? This discovery was cited as the birth of modern chaos theory. Weather systems are predictable. They are also chaotic. One of the most famous concepts popularized by Lorenz is the butterfly effect. And this idea suggests that the flapping of a butterfly's wings in Brazil could set off a chain of events that can lead to a tornado in Texas. Now, that might sound ridiculous, but, well, it's a metaphorical example. It illustrates the fundamental characteristics of chaotic systems. Small initial changes leading to vastly different outcomes. The butterfly effect encapsulates the sensitivity to initial conditions that defines chaotic behavior. Now here are the key concepts for chaos math. Deterministic nonlinear systems. That's number one. That's deterministic nonlinear systems. Number two is sensitivity to initial conditions. Sensitivity to initial conditions. Number three is fractals and strange attractors. That's fractals and strange attractors. Number four is bifurcation and period doubling. Bifurcation and period doubling. And number five is Lyapunov exponent. Lyapunov exponent. And that's Lyapunov. And you all know how to spell exponent. Now let's talk a little bit about each of these and get into some details. And if you have any questions, feel free to ask. Now let's talk about number one, deterministic nonlinear systems. Chaos arises in nonlinear systems. Now what is that? A system in which change is not proportional to the inputs, right? So as opposed to a linear system where cause and effect are directly related. A linear system is you put in here, it goes out there. A nonlinear system, that's not necessarily the case. The effects are often disproportionate. Most systems in nature, including fluid dynamics, weather, population growth, are nonlinear. Nonlinear systems can exhibit feedback loops where the output of the system cycles back as an input, amplifying changes over time. Okay? Everybody understand? All right. Doing well so far, and we're awake. It's very impressive. Let's talk about number two, sensitivity to initial conditions. We discussed this a little bit already, but as I mentioned earlier, chaotic systems display extreme sensitivity to their initial states. What happens on the front end is massively important. Even the most minute, the smallest of differences in starting conditions can lead to widely divergent outcomes. Think about certain things in the weather, right? The conditions that create what we call the perfect storm, tornadoes and things like that. That's something to think about here. This is why chaotic systems are unpredictable over long periods, right? Despite being governed by deterministic equations, because conditions are so sensitive. Number three, fractals and strange attractors. Chaos theory is closely tied to the concept of fractals, geometric shapes that exhibit self-similarity across different scales. Okay, so fractals often appear in chaotic systems as visual representations of a system's behavior. A famous example is the Mandelbrot set. Okay, that's an excellent example. It's a fractal that emerges from simple mathematical rules but produces infinitely complex structures. Okay, so strange attractors are another key concept in this. So there's the fractals. The strange attractors are in a dynamic system. An attractor is a set of states toward which something tends to evolve, a system tends to evolve. So strange attractors, unlike regular attractors, have a fractal structure and indicate the system's chaotic behavior. So, for instance, the Lorentz attractor is a well-known example. It never repeats, but follows a discernible pattern, tracing out a butterfly-shaped figure in phase space. Again, think about those ocean waves, right? That's helpful for visualizing this in your mind. Everybody understand that? I'm seeing some blank faces here. All right, I'm going to move on. Okay. Number 4, bifurcation and period doubling. Okay, so in chaotic systems, small changes in parameters can lead to sudden shifts in behavior, right? A process known as bifurcation. Now, bifurcation theory studies how a small change in one parameter can cause a system to change qualitatively, okay? Moving from stable behavior to chaotic behavior. In many systems, these bifurcations follow a pattern known as period doubling, okay, where a system's irregular behavior becomes increasingly complex as it shifts towards chaos. I'm going to read that again because this may be an important term for you. Period doubling is where a system's regular behavior becomes increasingly complex as it shifts towards chaos. Okay? Let's talk about the Lyapunov exponent. A key measure of chaos is this exponent. This quantifies the rate at which nearby trajectories in a system's phase space diverge. Okay? A positive exponent is an indicator of chaos, and it means that initially close states will exponentially diverge over time, making long-term prediction impossible. And for the Lyapunov exponent, there's a lot of reading I have in the selected text I've highlighted for you all in the syllabus, so please check that out after class. That might help significantly with the understanding of this. Let's move on. So applications of chaos mathematics. How can this be used? It's not just abstract math. This is directly applied stuff that impacts us every day. So meteorology is number 1. Obviously the study of physics, right? Physical symptoms, the motion of planets, the behavior of fluids. In turbulence, for example, this is an excellent example. Chaotic patterns emerge as fluid flow becomes increasingly complex. Okay, so similarly, chaotic motion can be observed in mechanical systems like the double pendulum. Everybody know what a double pendulum is? Right, so small changes in starting conditions are leading to wildly different motion. So that's a way we observe chaos in physics. Biology, biological systems, right? Study of life. These are often nonlinear, and they display chaotic behavior at times. Population dynamics in ecology can be modeled using chaotic equations. Small changes in birth rate or death rate can dramatically affect the long-term survival of a species. Heart arrhythmias or brain activity are other examples where chaos theory has provided immensely valuable insights. So that's another application. Economics. You can apply chaos math to economics, especially in modeling financial markets. Okay, so they're notorious for their unpredictability, and when conditions change, obviously the market, but economists once believed that markets followed rational, predictable patterns. Chaos theory has shown that markets are often chaotic systems sensitive to small fluctuations. I would like everybody to read up on their cryptocurrency, okay? If we want to talk about how chaos impacts economics and value. And of course, there's you can seek the impacts of chaos in engineering. So engineers use chaos theory and control chaotic systems in fields like robotics and telecommunications and electrical circuitry. In telecom, for instance, chaotic signals can be harnessed for secure communication, as the inherent unpredictability of chaos makes it hard for third party to intercept. So by adding a chaotic system into mainframes, you can create a higher level of security. So in conclusion, chaos mathematics, for me, it's a profound and fascinating field that reveals the complex, often hidden structures underlying systems that appear random. So from weather patterns to population dynamics, study of chaos demonstrates that deterministic systems can produce unpredictability due to their sensitivity to initial conditions, right? I'm going to say that one more time. Study of chaos theory demonstrates that deterministic systems can produce unpredictability due to their sensitivity to initial conditions. Okay, although long-term predictions are impossible in chaos systems, the patterns and principles discovered through chaos theory have revolutionized our understanding of the natural world and continue to have practical applications across various disciplines. And you're all asleep. Wonderful. First day of class and they're all sleeping. Well, class dismissed, I guess.